Alright, so let us begin. 2 after 2, 1, 2. Our Father, who art in heaven, hallowed be thy name, thy kingdom come, thy will be done on earth as it is in heaven. This day our daily bread, and forgive us our trespasses, as we forgive those that trespass against us. And lead us not into temptation, but deliver us from evil. For thine is the kingdom, power, and the glory forever. Amen. All right, so let us run through these questions. So, question number 1. Asks us to solve for x. So that's 125 to the power of 3x equal 1 over 5 to the power of 18. Right, so our aim is, when it comes out to this equation, our aim is to get the bases to be the same. So we must get the bases to be the same. And after we get the bases to be the same, we must get equal bases, equal number of bases as well. So by now, we should know that 125 is the same thing as 5 to the power of 3. Or we can divide 125 through by 5 to get a base 5. So we have to always keep the smaller base and then rewrite the larger base in the smaller base. So all of that is x. Now we go on this and this to be on the same level, so we have to rewrite this in another form. Yes, so we use the negative power rule, where we say a to the negative x, same thing as 1 divided by a to the positive x. So we're going to just rewrite this with a negative power to get it at one level. Because that's the only way we can say, okay, the bases are equal. Right, because this would be 1 over something, but we want it as just 5 to the power of something. Good. So applying this rule, we just rewrite this as 5 to the power of negative 18. Right. So now we are getting somewhere. So we can now go ahead and apply the power to power rule. So applying the power to power rule, we keep the base, multiply the powers, so we get 5 to the power of 9x equal 5 to the power of negative 18. So now we have the equal bases, so we can apply the rule where we drop the base and equate the powers. So what the rule states: drop the base, equate the powers. So we have 9x equal to negative 18. So now we can solve. 9 times by 9. So x there equals negative 2. And that is now solved. X equals negative 2. All right. X 2, 125 to the power of negative x times 5 to the power of x plus 3 is less than or equal to 5 to the power of 0. So again, we apply the rule. We must get the basis to be the same. So 125 is equal as 5 to the power of 3. And since 125 is raised to the power of x, we have to raise that to the power of negative x. 5 to the power of 3 is the same as 125 times 5 to the power of x plus 3. Less than or equal to 5 to the 0 power. Work that one out, sir. Pretty much. Go ahead and we apply the power rule. So we have 5 to the power of 3 times negative x times 5 to the power of x plus 3 less than or equal to 5 to the power of 0. Please remember the rule that we must have equal number of bases on either side of the equation or in the equation. So when we look at this, we do not have, while we have equal bases, we do not have equal number of bases. Because over here we have what? 2 base 5. Over here we have only 1 base 5. So we have to make sure that we have equal number of bases. So we have to reduce this to only what? 1 by applying the first law. Multiply two quantities with the same base. We state that we keep the base and add the powers. It's negative 3x plus x plus 3 less than or equal to 5 to the power of 0. Right, so what to do from here, sir? Now the bases are the same and equal. So we just drop the base, equate the powers. So we have negative 3x plus 3 is less than or equal to 0. And that's the power there. So we go ahead and solve that in the equation. So negative 3x plus x leave us with negative 2x plus 3 is less than or equal to 0. So what do I do from here, sir? Bring over the single term because we are solving the single equation in the equation. So we bring the single term over. So we have negative 2x less than or equal to negative 3. Bring the 3 over, it becomes negative 3. What do from there, sir? Solve for x by dividing both sides by negative 2. Now, this is where some person will have missing to know. You have to remember that once you divide an equation by a negative number, you have to reverse the sign. So this cancels out. So x now reverse the sign greater than or equal to positive 3 over 2. Because when you divide two negative numbers, the result will always be positive. Just like that. Maria, follow me so far?
Yes, sir.
Pretty much that is the value, range of values of x. Because when it comes on to in the equation, we have infinite number of values. All right, so our focus now is now drawn to this new topic called function, relation, functions, relations, and graph. Now we will just focus on one aspect of a function, relation, and graph. We will just focus on the aspect functions, relation, and graph. Now, what is a function? A function is a relation in which each element in the domain is mapped onto one and only one element in the range, or we call it the co-domain. I repeat that. A function is a relation in which each element in the domain is mapped onto one and only one element in the co-domain. And if you notice in brackets, I put range and I put an asterisk beside it. Now, that asterisk is there. I am indicating that codomain and range, they are not the same thing. They are different. They're not the same thing. Codomain and range. However, you will not know, you will not deal with question as it relates to differentiate between the two unless you are doing K math. So CXC permits you at this level to just call it range, but there's a slight difference between the two. So from now on, we will just work with it as range. All right? So since a function is a relation, then the question is, what is a relation? Because a function is a relation. Now, when it comes down to a relation, we said that a relation is a set of ordered pairs which or that obey a particular rule. So it must obey a particular rule. That is what we call a relation. It's a set of ordered pairs which obey a particular rule. Now, let's talk about an ordered pair. Since a relation is a set of ordered pairs, let's show you an example of what a set of ordered pairs is. It's a set of ordered pairs that or which obey a particular rule. Now, an ordered pair consists of what we call the x and y coordinates. That is what an ordered pair is. It consists of a set of x and y coordinates, right? And for example, the x is always the coordinate that comes first, and y is always the coordinate that comes after. So it is a set of ordered pairs that obey a particular rule, right? That is relation. This is ordered pair. Now we said that that each element in the domain is mapped onto something, onto one and only one element in the range, or we can call it the codomain. What's the domain? So that the domain, so we're talking about the domain. The domain is the same as, say, your x coordinates or your x axis. That's your domain. And your range is the same as, say, your y coordinates, or we can say the same thing as your y axis. So this is what is meant by those terms, domain and range. Now, your domain is always given every time. It's always given. So even when it comes on to a graph, CXC will always give you the domain. The domain is what they call your independent variable. It does not depend on anything. Does not depend on anything. That's your independent variable. It is always given. It's always known. And then your y coordinates now is always referred to as your dependent variable. It always depends on the y. Sorry, it always depends on the x. So without the x, you cannot know what y is. It is essential. It is necessary to know that. All right? And this now is called your Cartesian plane, or your x and y plane, where your x-axis goes across, your y-axis is vertical. Now these are different names used for your x-axis. You have, it is called your domain, and it is also called your horizontal axis. Right? Called your horizontal axis. And your range is your y-axis, otherwise known as your vertical axis. otherwise known as your vertical axis. All right. So these are key information that you need to know as it relates to functions. So I want you to bear this in mind now. This definition, we are going to look at some relations, and it is very, very important to look at the reason for that. CXC loves to give you these things on the multiple choice, and they love to give you these relation diagrams and ask you to determine whether it is a function or not. CXC loves to do that. So let me erase slide. Let me see if I did that. Negative 3x plus 1x, subtract the sign of the larger. So that's how we get negative 2x. Can I erase? Or we can just extract it from the root. Now we are going to look at some relation diagram. We'll look at some relation diagram. Now, first, in fact, there are 4 relations as it relates to functions. And not all relations are functions, but we can say that all functions are relations. So let us look at the relationship that exists among these different rules that we're going to look at. So we're going to first look at what we call a one-to-one relation. One-to-one relation. See diagrams like these on the charts. Your domain, your range. Said that the domain is the same as your x-axis, range is the same as your y-axis. Now, since the domain is always given, let's look at the domain here as 5, 8, 11, 13. So these are, so that these are your x coordinates. Domain, same as saying your x coordinates. Right, so it is always given, even when 6 is given graph and they give it in table form. the domain, they always give you the domain every time. Always give you. All right. So let this be the rule. 2x plus 1. So 2x plus 1 is the rule that will map x onto y. So for now, I'm calling it a rule, right? When we finish look at the rule, then we will determine if this is a function or not. But as the definition tells us, that a function is a relation in which each element in the domain, and this is the key part, is mapped onto one and only one element in the codomain, or for now, we just call it the range. That is the key point you have to remember. If you do not know what a function is, then you say, give us some relation diagram and ask which of those diagrams represent a function. Then you will be clueless. You have to know what a function is. All right. So let's do the mapping. So the mapping that we're going to do, we're going to plug each x coordinate into the rule, because that is what you will do when it comes down to us doing graph. That's what we will do. All right, so we're going to plug each x coordinate into that function, work it out, and whatsoever we get, that is what should come over here. So 2x means 2 times x, and 2 times 5 plus 1. When we work that out, how much we get? Plus what? 2 5s, 10 plus 1, 11. So right away, we see that 5 is mapped onto 11. Same thing. But for 8, plug in 8. 2 times 8 plus 1, 2 8s, 16 plus 1, 17. And we do the same. Next one. 2 times x, which is 11 this time, plus 1. We say 2 times 11, 22 plus 1, 23. So that must map onto 23. Same thing for that. So we say, all right, 2 times 13 plus 1, 2 times 13 give us 26, 26 plus 1, 27. All right. So as you can see here that each element in the domain is mapped onto what? One and only one element over in the range. So when you have a mapping like this, 1 to 1, each element on the one map onto another, then question, is this relation a function? Based on definition, is that relation a function? Yes, it is. So we can conclude then by saying that this relation, which is really a one-to-one relation, this relation is a function. All right. What would be the order pair here? So let me show you what would be the order pair in terms of the coordinates. The Order pair would be 5, 11, 8, 17, 11, 23, and 13, 27. So we say that this always represents the x coordinate, that always represents the y coordinate. So it's x and y, x and y, x and y. And sometimes on the multiple choice, CXC give you a set of coordinates and ask you which set of coordinates really represent a given the given function. So they give it a function. In this case, I call it a rule. They give it a function, and then they give you a set of coordinates and ask you which set of coordinates basically represent that function. And how you have to work it out, you will have to plug in each x value in the function, work it out, and see if you get the corresponding y coordinates, and that is how you determine it. But we will work those questions when we look at multiple choice. But those are multiple choice questions. All right, so it is clear from definition and from illustration, it is clear that this relation is a function. Why? Because it is clear to us that each element in the domain is mapped onto one and only one element in the range. And that is what makes a function a function. So let's look at relation number 2. So this relation that we are going to look at is what we call a many to one relation. So we are going to look at what we call a many to one relation. So for this relation, go ahead and just say domain and range, as it were, x and y. All right. All right. So we have domain, we have range, right? So this time, these are the x coordinates. So we have 0, 1, 2, -1, -2. So the domain is always given, every time. It's always given. All right? And this time, the rule that map x onto y, I'm going to make this rule be x squared. So that's the rule that will map x onto y. So I'm not going to call it a function as yet. I'm just calling it a rule because we want to know if this rule is really a function. So we are going to do the same thing that we did over here, where we are going to plug in each x coordinate in the rule, work it out. What we get, that's what it will map onto. Right? So let me start with smaller one, 0. Well, not the small one, but let's start with 0, as these are small. Let's start with 0. So if I plug 0 in, that become what? 0 square, not true? Plug 0 in, that becomes 0 square. So if we square 0, what result do we get? That's 0 square. 0, exactly. 0 squared is 0. So it is clear that this 0 up onto the 0. So it's very clear. All right, let's plug in 1. So we plug 1 in that rule, that become 1 square, and 1 square is 1. All right, 1 square is 1. So let's plug the 1 over here. 1 square, so we square 1, and we get 1. So 1 map onto 1. Right. Then we square 2. 2 square give us 4. So 2 here map onto 4. So let's plug -1 in. So when we plug -1 in, what is -1 square? Still 1. Once we square a negative number, the result is always positive. So -1 square is still 1. -1 map onto 1. Let's try that for -2. So we plug -2 in. -2 square gives us +4. Good. So -2 as well is mapped onto 4. So the question is to you, is that relation a function? Based on definition. That's not reading, or you just have to find it. No. Is that relation a function? I hear yes, I hear no. That's right. So yes, it is a function. Let's see how it is a function. Let's trace it. And that is why I am focusing on this. Remember that each element in the what? In the domain. So this is your base. This is the base is your work from. Because it's always domain that maps onto range. So when we come over here, our domain, let's check it out. If I look at this element, how much element is mapped to over here? 1. What about this one? Still 1 element, that's true. It maps onto. What about this one? Still 1 element. What about this one? Still 1 element. What about this one? Still 1 element. That's the key. Each, and that's why it is called what? Many to 1. So you can always look at it from that point of view. Many to 1. Many to 1. That's the function. So we can say then, so we can conclude by saying that this relation is a function. We can bank on that. This relation is a function. Now, let me explain it from a different, from a practical point of view. I'm going to use this principle that we teach in advanced mathematics called the pigeonhole principle. And it is so easy to relate to. It is called the pigeonhole principle, where we have a set of pigeon, a set of pigeons, all right? And over here, let's say we have the holes. Now, let these represent the pigeons. And these represent the holes. So we are looking at that principle called the pigeonhole principle. Now, this principle states that if you have more pigeons than holes, there exists a hole, at least one hole with more than one pigeon. So let's look at it from a practical standpoint. So let's say this pigeon flies into that hole, and this pigeon flies into that hole, and this pigeon flies into that hole. Do we have another empty hole? No. So these two pigeons is going to just fly into a hole because they too want to go into a hole. But the fact is that each pigeon flies into a hole. That's the principle. So even though this and this map onto the same element, it does not change the fact that each element over here still maps onto one element in the range. So you can always look at that pigeonhole principle. So if you have more pigeons than holes, there exists a hole, at least one hole with more than one pigeons in it. Because each pigeon will fly into a hole. These two will not stay up. They are going to fly into a hole. So we call that. So we call that the pigeonhole principle. We use that principle in advanced mathematics. It is simple to explain this to you, so it's more practical to relate. All right, so we can conclude then by saying that that this relation, which is a many to one relation, is a function. Yes, we can say that. Samaria, so far?
Yes, sir.
All right, so we are going to look at the other two relations. Can I trace on that side? Yes. All right, so look at, can I erase this side, right? So just bear this in mind that each element in the domain is mapped onto one and only one element in the range. And that is what makes the relation a function. Right, so bear that in mind. See, when you understand these principles, you will not find functions difficult as how you found it before. All right, so the next relation we're going to look at is what we call a one-to-many relation. So that's one-to-many we're going to look at now. So just look at many to one, so we're going to look at one-to-many. So domain, range. X, Y. Now this time I'm going to make the rule be, so the rule that maps X onto Y, be the plus and minus square root of X. We take in the plus and minus square root of X. We are going to make X, since X is always given, we're going to make X be 0, 1, and 4. We're going to make X be 1, 0, 1, and 4. And we're going to use that rule to map X onto Y. Now, this is not strange to you because you have seen something like this since we have done quadratic equation. You have seen that in the quadratic formula where you have the plus or minus square root, because in general, when you take the square root of a number, you are really taking both positive and negative square root. It is just that most questions they ask you for just the positive square root, but in general, you are taking both plus or minus square root. All right, so we're gonna plug that in, each value in, and see what we get. All right, so let's plug in 0 first. Now it means that we're gonna take the positive square root of 0 and also the negative square root of 0. But whether you take a positive or negative square root of 0, the result will still be 0, because 0 is neither negative nor positive. So just put a 0 over here. So 0 maps onto 1 to 0. Let's plug in 1. So we're going to plug 1 in. So we're going to plug in 1 now because the square root of 0 is 0. So let's plug in 1 and let's plug in 1 because that is what it means. Taking both positive and negative square root of 1. Now, when we take the positive square root of 1, what are you going to get? You're going to get a positive 1. When you take the negative square root of 1, what are you going to get? Negative 1. So in general, whenever you take the negative square root of any number, the result will always be negative. Whenever you take the positive square root of a positive number, then the result will always be positive. Well, it is impossible for you to take the square root of a negative number. It does not exist. Try that, the calculator is going to say syntax error. You cannot take the square root of a negative number, but you can take the negative square root of a positive number. Right. So let's fit this in now. So we're gonna have a positive 1 and we're gonna have a negative 1. So the positive square root of 1 gives us positive 1. But the negative square root of the same one gives us negative 1. What's happening there? Let's try it for 4. Take the positive square root of 4 and the negative square root of 4. This is going to give us a positive. This is going to give us a negative 2. So we have a positive 2, negative 2. So basically the square root of 4 is going to map onto 2, but it's also going to map onto what? Onto negative 2. Now, based on definition, is this relation a function? No, it's not a function. Why, sir? Because while this element mapped onto only 1, we still have there exists at least one element that does not map only onto 1, because this maps onto 1 and it maps onto negative 1, and that would basically go against the rule of what a function should be. So this relation is not a function. We can conclude that this relation is not the function. All right. So this brings us then to our next relation diagram. In fact, before we look at the next relation diagram, there is something I want to bring out. There is something I want to bring out as it relates to domain and range. All right. Now, when it comes on to relation diagrams, there is no law that states the domain has to be on this side and the range has to be on this side. So sometimes you will look on the multiple choice paper and you may see something like this. And I really want to ensure that it is clear to you. You may see something like this, where they do not indicate which is domain by writing and which is range, but they will do something like this. Yes. They will do something like this. And you may look at that and wonder, wait, which is domain and which is range? Now, this I do not want you to miss. They normally use an arrow. they have to use an arrow. Because drawing just a ray like that indicates nothing. So they have to use an arrow. And the tail of the arrow is always represents where it is coming from. And the head of the arrow indicates where it is going. So in other words, the tail of the arrow always represents the domain. And the head of the arrow always represents the range. Why, sir? Because it is always X that maps onto Y and not the other way around. And that is why your domain is always referred to as your independent variable, because it is always given, it's always known. It depends on nothing. But Y always depends on X every time. And you will see it as we go further and further in this topic. So it means that it is possible that the diagram can look like this, where the domain is on the right and the range is on the left. This is totally different from when you write a pair of coordinates. When you write a pair of coordinates, X always comes before Y. So that is when you write a pair of coordinates. Or if you should go on your graph, then X is always the horizontal axis and Y is always the vertical axis. But when it comes to you just writing a relation diagram on a plane, because this is called a plane of that surface, just writing a relation diagram, if the order does not matter, your domain can be on any side. Are we together with that one? All right. Maria, follow me so far.
Yes, sir.
Okay. All right, so let's eliminate this. So let me just, before I look at the last one, let me just make a quick view. Let's review. A quick review. All right, so in reviewing, looking at the relation diagram, we see there are 4 types of relations, and we know we have now looked at 3 of them, but there are only 4 types of relation. Right? Now, the first one we look at is what we call a one-to-one relation. And a one-to-one relation, we said that that relation is a function. That is what it is. It is a function, a one-to-one relation. And we say that how it becomes a function, because we say that a function is a relation, but the relation is such that each element in the domain is mapped onto one and only one element in our range. Like what we see it here, 5 only up onto the 11, 8 onto 17, 11, 23, 13, and 27. It only mapped onto one and only one element in the range. All right. And we said that this relation is a function. We look at the many to one, as the name suggests, many to one. That's the relation. We say in this relation, you can have more than one element in the domain mapped to the same element in the range. And it does not change the fact that each element in the domain is mapped onto one and only one element in the range. We use this principle called the pigeonhole principle, that if you have more pigeons than holes, we say that there exists at least one hole, that will have more than one pigeon in it. Because each pigeon flies into a hole. But even though a hole may have or contain more than one pigeon, it does not change the fact that each pigeon flies into a hole. That's the principle. All right, so, and then we just look at the many to one relation, and then looking at the many to one relation, we would have concluded from this relation that it is not a function. And how we know that it's not a function? Because each element over here, we have at least an element here that maps to more than one element in the range. And now, class, this is why it is important that it is always the domain map onto the range. Because if you should look at it from this point of view, from range to domain, may appear to you that it is a function. Because if you're going to look at it from range to domain, then it would signify that this map onto one, this map onto one, this map onto one, that map onto one, and so on. And if you look at it in that sense, you are going to lead to the wrong conclusion, saying that it is a function, but it is not. Why? Because the mapping is always from domain to and not range to domain. Very, very, very important. All right. So let's look at the final relation. All right. So in this relation, I will not use numbers. I will use fruits and colors. So we call this a many to many relation. Many to many relation. All right. So with a many to many relation, let me draw it very rectangular. So we're gonna have over here, we're gonna have fruits. Over here, we're gonna have colors. Fruit, colors. So we're gonna have fruit. Green, mango, apple, banana, green, apple. So let me put over here. Let me put colors like red, black. Right, so here we have some fruits and we have some colors. So we're gonna have fruits mapped onto colors. Right, so we can have, so let's work with the banana. What colors we could map the banana onto? We map onto yellow. We could map onto what? Oh, see, all right. We got that is green. So we can map onto yellow and we can map onto green, right? It's about the green. Green can be green and some black natural. Some black. Alright, what about the mango? You have red grapes, is that true? How about mango? So mango can be green, it can be what? Red, and it can be yellow. How about the apple? So it could be green, it could be what? Black too, our OTT apple. Right, with black natural. They said I want the black one. Our local apple, and at times it ripes so much to the one, to the look black. I said, is the black one we want? And it can be red as well, not true? Alright, so basically you get this scenario, and just like even looking at this, does that look like a function to you? But it look like confusion, that's true. Look like confusion. So by the name, many to many, by the name, suggest to you that that relation there is not a function, right? So we can say that this relation is not a function. And these are the four relations that you, relation diagrams that you will always come across. All right, so let me just shut that in. That's ready. Now, so we are going to conclude. So from this, we can redefine what a function is. So maybe you have not done it like this, but we can now redefine a function. So in conclusion, we can say that. So we're looking at conclusion. So we are concluding now. One can say a function is a one-to-one or a many-to-one function. These are the only two relations that we see. These are functions. Sorry, the relation should be, sorry, the one-to-one or many-to-one relation. That's not relation. All right, so that is in summary. And then we can also conclude that all functions are relations. Some relations. All functions are relations, but not all relations are functions. And we see it clear here that a one-to-many and a many-to-many relations, they are not functions. But all functions are relations. Not all relations are functions. Now, this sets the groundwork for what we are going to launch into next class. We will be looking at how to evaluate functions. We will also look at rational functions. We will look at composite functions, and we will look at the inverse of a function. But all of what we would have explained here, it sets the foundation for what we will be going into the next class. And then after we have finished with evaluation of functions, then we can go into the graph aspect of functions, which is very, very straightforward. It's all about just plotting a few points and connect them. That's it. So graphing is not difficult as one may say is. When we get there, you will see it for yourself. Um, in next month, I am going to, because I would normally keep a early marathon, as I did mention before, to run through two compulsory topics on your exam, which you know that vectors and matrices, they are must. So I will keep a marathon, run through these things and as much of vectors as we can, so that you can at least have the knowledge in those topics where you can practicing. Right? So there, right? So this is where